Linearization, sensitivity, and differentials. Blah, blah. Linearization, sensitivity, and differentials. Linearization, what? Line. Oh, tangent line. Using the tangent line to approximate local linear approximation. Using the tangent line to approximate. This was an application of derivatives from last year. You guys definitely saw it on AP practice. Should have seen it probably at least once on the AP. Would have been in multiple choice for sure, not FRQ. Linearization, local linearization, local linear approximation. All of it, what does it have in common? Line. Which line? Tangent line. Why did I go over number 17? Well, A to be nice and B because it ties in with section 5.5. Y minus y1 equals, wait, that's not what you see. What did they just move? They just moved the f of a. And they just renamed y to be L of x, standing for line. Okay, that's cool. So they named y L of x to represent the tangent line itself. Just a quick sketch. It's not a big stressor. Unless you guys want to make a note of this to help you on future problems like number 17, you could be super snazzy and be like, hey, if they give me some other point on the line, that the line like goes through somewhere else, I could call that like an x and a y. It's not going to be my a and f of a, but maybe, I don't know, maybe it would help for you guys to be like, any other point on this line is just an x and a y. But it can't go in the a, f of a, f prime of a spot. Maybe that would be helpful. But without having that specific problem in mind, I'm not sure you would have really understood what I meant if I just wrote an xy some earlier point in time. But a tangent line skims. It skims at a point of tangency. It has the point slope form of the equation. They just got the line, the L of x, the y by itself. Okay, cool. So what's going on? Tangent lines will be really good approximations, pretty good, fairly good approximations of y values, very, 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 very close to the point of tangency and not necessarily anywhere else. Now, there might be some sort of accidental somewhere else where it gets close to the curve. The curve comes back down for a little bit, but you won't know that. You won't know that well anyway. Without having a full picture of the original function and the tangent line, that's never going to happen. But we can say the tangent line gets an approximate and a fairly good approximate for values really, really, really close to a. Which means we can use the tangent line. We can use L of x to approximate y of x. So the idea of local linear approximation is that L of x can approximate f of x. Now, I'm not saying it's always a good approximation. It can approximate anywhere. It's going to be really far off, though, for any curved graph, anywhere but the region very close to a itself. But the idea of local linear approximation is use the tangent line to approximate the values of y. So, if they give us the problem, find the tangent line approximation of 1 plus sine of x at the point 0, 1. Now, I'm not going to necessarily go to our calculators and use the table. We could. But how would we accomplish that problem? What do you need from it, bud? Here, let me grab the pen, just to save you time. All right, guys, make me a tangent line at the point 0, 1. There you go. Make me a tangent line at the point 0, 1. That's okay, that's the point of tangency. That's not just some random point somewhere else on the line. It's not saying that the line goes through 0, 1. You see the difference? It's not saying it just goes through, it's saying the tangent line. This is the point of tangency. This is my a and my f of a. Just because we're trying to get you guys to your homework questions sooner, are you guys okay if I do y minus 1 equals f prime of 0 times x minus 0? Are we good? Okay. And my f prime, we all know, that's just cosine, yeah? And so when I go to plug in, I get y minus 1 is equal to cosine of 0 times x minus 0. Hence, I could call my y, in keeping with the book's notation, we'll just replace y with L of x, talking about a tangent line. Sure, why not? Y is of that line, equal to 1 plus cosine of 0. Okay, that's my tangent line. Are we okay? So what if I was to ask you for, hey, cool kids, can you approximate? One plus sine of 0.1. Could you just do that off the top of your head? No. But what can you do with the tangent line? You can say, hey, isn't this the same thing as f of 0.1? So can't I take the x of 0.1 and say, oh, hey, I can put it in here and it's going to be maybe close. Why is it maybe going to be close? Where's my point of tangency? 0. And how far off am I from 0? Not far. So then we can go ahead and plug in. Someone grab out your calculator. Someone in here is bound to have it. My L of 0.1 is going to equal 1.1, which we are saying is some sort of a sine of 0.1. See how close we are. Ooh. Now, is it a great approximation? 1.001, 1.002. It's not great. Why? Yeah, the slope's different. So maybe there are going to be better ways of approximating as we go through CalcBC. There are. But for right now, is it an approximation? Yeah. Can we use it? Yeah. Is it great? But it's something, right? What's going to happen if I were to go to 0.2, 0.3, 0.4? What's going to happen as I get farther and farther from 0? Yeah, it's probably going to get less and less and less accurate, more and more and more off, right? It's probably going to get less and less and less accurate, more and more and more off. But what if I was to go to 0.05 and 0.01 and 0.001? What's going to happen to my approximation? It's going to get closer and closer and closer. So wait a minute, how on earth am I able just to give you guys that and say approximate the following roots, please? Because you're a genius and you can do the square root of 123 in your head? Go team! No! Can you approximate? What would be a reasonable answer? Mrs. McCrae, I sat in on her class today, period 2. She's my hero, Math 6, teaching kids to approximate answers before solving so that they know if it's actually in the right camp or not. Where would it be in between? Okay, good. Guess. No. Use a tangent line. Oh, how? Is it closer to 11 squared or 12 squared? Closer to 11 then, right? So where do you think I want your point of tangency to be? What's your function? Got it. So can't we do f of x is equal to the square root of x at 11 and 121? Pause. It's not the right way. Hold on. Who's my x? Plug in 121 and get out. Go. And then once you find that one, go do the exact same thing on letter B. But you have to kind of change it up a little bit because it's a different kind of problem. You can approximate roots of anything. It's just going to be a better approximation if it happens to be close to a perfect square or a perfect cubed or a perfect fill in the blank that you do know. It's going to be farther off the farther away you get. Give you guys a little bit of a head start, but not too much. Yeah. Does that make sense? Good. Did you guys hear Riley? just in case I lost anyone, filling in why I did what I did. So the square root of 123, which is f of 123, will be approximated by the tangent line at 123, which, plug it in, plug it, oh, I don't know that. Oh, but you could. I'm not saying you like it, but you could, right? Two over 22, what's that? 2/11ths, right? No, 1/11th, right? Good. Which is equal to, which is an approximate of 123. Because 11 goes into 0, and then 9. Does it go 0, 9, 0, 9, 0, 9? Yeah. Which is the tangent line, which approximates. Who's already plugged in 123? Square rooted. Ooh. Go team. So plugging in 123 to the x value, because remember, this is my f of. We just had to figure out what the f was of. Then we plugged it into the x spot. I went ahead and got y by itself after I plugged in. 123 minus 121 is 2. 2 over 22, 1/11th. 1/11th as a decimal. And what Aryan just said, square root of 123 is 11.0905. Ha-ha! Go team. But wait, pause. Think about the nature of the square root of x. Why is this approximation so much closer when it was 2 away, whereas the one a second ago was 0.1 away and it was so far? What's the curvature of square root of x doing? What are the slopes doing? The slopes are decreasing and, in essence, approaching 0, right? So what's happening to that tangent line? It's getting closer and closer and closer to the curve for longer and longer and longer intervals, which means because of this curvature, this tangent line will be a better approximation for longer, whereas sine, what's true about his curvature? Ooh. It's a lot steeper, especially at 0, because that curvature deviates much quicker than the curvature would deviate from the line of the square root of x. Oh, are we a better approximation? Oh, okay, that's even better. I wondered why it was so far off, but I was like, well, I guess it has a lot of curvature. Thanks, James. Did you guys keep going on letter B? What's your f of x? Cubed root. You guys came up with the point that was close. Ooh, cubed root of 27 is 3? That's a good point. Just think, anyway. Thank you. Wasn't even planned. Best ones. Although no one laughed until I said something. It's okay, you're focused. Now, is it normal that the AP makes you come up with your own problem? No. But is it cool that you can come up with your own parameters based on a given piece of information and use calculus to approximate? It's pretty cool. If you finish before we do, go throw it in a calculator and see how close you are. 2.037? No. Oh, 2.9. Sorry. I didn't subtract. That was my bad. That'd be a negative 2.9963, approximately. What's the actual cubed root? Ooh. Okay. Not too shabby, huh? I really like tangent line approximations because it gives you like a very tangible, like, here's a problem, there is a calculus way of approaching it, and then trying to approximate. Anyway, I think it's nifty. But guys, what was the title of section 5.5? And there's 3 other parts to that title. What's the next one? Sensitivity. What's the last one? Differentials. Sensitivity. Have we already talked about sensitivity this year? When? I lost all of you, and I don't know why. Sensitivity. Oh, we talked about it. Do you remember? Yeah, anesthesiologist with medication. Remember, we were talking about how your body would affect different dosages based on, well, we didn't really go into tons of detail. We talked about sensitivity in that way. So what's going on now? Differentials first. I'm trying to be nice. I didn't even cover sensitivity. Well, you might see it again. I don't know why. I mean, we already took notes on sensitivity, so maybe I think it's okay. Interesting. I don't know why I didn't put sensitivity in there. Well, you're going to see sensitivity again. The nice thing is sensitivity, it was approximated by a derivative. So I think this is the section of approximation. So I guess it makes sense they would bring sensitivity back. It wasn't even that hard. It was literally taking a derivative. And it was based on, like, was it body temperature and dosage? Or dosage and weight? I don't know what the function was. We were basically approximating the sensitivity. I think it was per, like, milligram of a drug, based on taking the derivative of a function. So maybe that's why I don't think it's going to be a big deal. But I did bring back differentials. Yeah. And so sensitivity approximates, tangent lines approximate, and then differentials approximate. Too bad you guys didn't have like a calculus-based chemistry class. That'd be fun. Okay, fine. Take a calculus-based physics class in college and you'll have something similar. Yeah, there's little baby bits. Party poopers. Oh, that makes sense because it's pretty physicsy if it has to do with light.
Yeah, you have to like measure the absorbance of like electrons,
Just keep saying words like that, Riley, and I'm like, it's good. So guys, how easy is differentials at its core as far as solving for them? Yeah, because all we're doing is dy dx and moving dx to the other side. It's kind of like just, I don't know, u sub with integration, right? Although we're not going to kill any bunnies on this one, right? Left a scar. I left a scar. You know what's cute this year for AB? I'm having them repeat after me. I'm saying, don't get tricked by the trig notation. And they're supposed to say, I won't get tricked by the trig notation. Anyway, why am I saying that? Because who's your outer? The squared, not the sine, right? All right, just double checking. So we have 2 sine of 5x, cosine of 5x times 5. So you guys totally understand why I'm about to say 5 sine of 10x, right? What property did I use? Double angle property of sine. 2 sine u cosine u is sine 2u. All right, well, that's fun. Anyway, double angle of sine, forever card number 1. That's all right, no judgment. Maybe a little bit, but that's all right. And then a product rule down below. Should I give you some nasty ones just to make you think? What's the derivative of 3 to the 2x?
Oh, just 3. Oh, 2.
Bulimbu, where are you? Bulimbu! Where is it? The limb, ln of 3. Ooh, u prime. Then you need your dx on the outside, right? We're just going to box that, stick it to the man. But hopefully you guys would have looked and said, like, hey, there's a 3 to the 2x in both of them. I'll pull him out. Anyway. There's no... That's hilarious. Cracking me up. Cracking me up, Smalls. That was pretty good. So kiddos, dy is just solving for a derivative and then moving dx to the other side. dy is just solving for the derivative and moving dx to the other side. What just happened? No. We talked about it last year. It wasn't really an Endeavor card. I don't think I've really seen it, this application on an AP anything. But you will see it in homework just a little bit, because it is, once again, where calculus gets a little practical. They kind of stick with the linearization estimation, though. And in CalcBC, we have other ways of estimating with. We'll get there. But the very end, how differentials actually get applied. The difference between estimated measured error versus actual, you can make a little proportion in the sense of actually subtracting the change in y's and approximating that with dy. So the idea that dy can be used to approximate. And so as you guys go on that, I'm going to go ahead and play around with this example just a little bit to show you, because I don't think you really need me to walk you through. It's more just seeing it and being like, oh, that's what you mean. What? Propagated. It's kind of like the resulting error. I'm sure the dictionary definition would be a little different. But if your measurement is a little off, like let's say you're using a tool that measures by tenths, like a ruler. If you're measuring by tenths, couldn't you be like up to a tenth off? I mean, hopefully you wouldn't be more than a tenth off, but you could estimate wrongly. Or your tenth should be accurate, I should say. Like your tenths place should be accurate, but your hundredths will be off. So then if you have a certain measurement error, how is that going to result in error of whatever you're plugging it into? Does that make sense? Positive number. Let's do it this way. Only if you need it. So let's say you knew your measurement error was 0.01. It was within a tenth, or I should say it's within 100th of the actual measurement. The propagated error would be like, okay, plugging in how far off you could be minus the measured value. Let's say you measured it to be 1, but you could be up to 100th off. So what's the difference between those two? Depending on the function, that could be really hard to find, but it'd be a lot easier just to plug in your measurement and how far off you are as the differential. And so the idea is they were saying compare the values. So once again, we compare 0.01 times 2 would be 0.02. That's what differentials would tell us as the approximate propagated error. But if we were to actually solve for it by hand, well, that'd be a little bit messier, unless you had your calculator. Hey, they were learning this in Math 6 today, how to multiply decimals by decimals. Technically, it's absolute value because it could be above or it could be below. Some of these problems have like a plus or minus as far as the change. It's not a very good approximation. Doesn't make sense, right? There are 4 decimals, though, true? Oh, that's funny. Look, there's a 0 in the second column, or in the second. That should have been 2 zeros. I wondered why that was so weird. 1, 0, 2, 0, 1. There we go. That makes so much more sense. So that minus 1 would be 0.0201. Yeah, that works pretty good. All right, kiddos. Whew. With that, we're done with section 5.5. Took a little longer than I thought because I forgot there was propagated error at the end. But let me go ahead and do this. I'm going to go ahead and go to your guys' shared folder. With homework due tomorrow. I'm going to go ahead and go to your shared folder. I'm going to show the even answers to everything we need. Now, question, did we grade 5.3? With maxes and mins? Okay. So I'm going to go ahead and get the answers to 5.4 up there. So that way tomorrow when we go over questions to 5.4, which is going to be lengthy, and 5.5, which should be short, hopefully. 5.4, which is going to be lengthy. 5.5, which is going to be short. I'm going to use you guys completely as volunteers to get you to the boards to pull them out. This is one that we've gotten slowed down this year that we went much faster last year is on homework questions. Because I've been trying to answer your questions and I need to stop that and get you guys answering your own questions. Well, each other's questions. So let me go ahead and get the evens up here on the board. It's going to be at the end of the video if you guys need to check it out later at any point in time. Some of you might be able to keep up with us now, but some of you might need to come back and look at the video. It's going to be on there at the very end of class today. But tomorrow come in with informed questions, meaning like, hey, I did the work, I got stuck, I checked with the odds or I checked with the evens on the video, and here's exactly where I'm stuck, why I'm stuck, etc. So number 2, final answer ended up being the largest possible area is 25/4. And the dimensions are 5 over root 2 by 5 over root 2. It's a square. Not a square, sorry, it's a triangle. It's an isosceles triangle. 25/4, 5 over root 2 by 5 over root 2. Number 14, 96 feet per second was A. Max height was 256 at 3 seconds. Yeah, hopefully, right? And then the velocity at 0 ends up being negative 128 feet per second. That's good. Profit. Profit. Did they give you the function? I feel like you had to make it yourself, didn't you? You might want to write down the function if you didn't get that one. But the critical point ended up being at 50 plus c over 2 or 100 plus c over 2. And that's going to be the same place as the maximum because of the simple sign chart. You could have the increasing, decreasing, realize what's going on before and after without going into economics at all. And that's enough justification to say that will be the selling price of the maximum profit. But you definitely had to get that profit function and then take its derivative, remembering that B and C and A are all constants and keep track of those. Oh, I gave you guys a lot of odds. Oh, yeah, I really wanted you guys to be able to check and know what you got right or wrong. We have a couple seconds, not a lot. Is there one in particular that you guys were like, we didn't even know how to start? I can give you a hint. Oh, it's on the calendar. Oh, for that one that you just got? No. It'll be due after the test, so probably after retreat. Because test is Friday. 27? Let's peek at that one. I heard that one a lot. Number 27. You have to make a piecewise function. You have to make a piecewise function. Use 50 as your separator for less than or equal to 50. Wait, if 50 people go on the tour. Yeah, maybe I'll post in Google Classroom the equation for 27. That sound good? Okay, I can do that. I'll post a class comment underneath this assignment for number 27. You guys can peek at it. Come tomorrow with questions on 5455, and we're going to have a big ol' half a class being a work period. And Kathy and Sally, your Nutella strawberries will be tomorrow. I didn't get to the store last night. Sorry, guys. Don't worry about test corrections until after.